In this video we're going to discuss solving rational equations. So the word rational has the word ratio in it. Ratio can be written as a fraction. So we're looking at equations that have fractions in them, and we've dealt with those before, but the variable was never in the denominator. So a rational equation specifically is one where the variable is in the denominator. So here are the steps. So first thing we're going to want to do is factor all the denominators. Some of them may not be able to be factored, but any of them that can be factored, we should factor. And then we're going to multiply both sides of the equation by the least common denominator. So we often talk about the least common denominator when we're trying to write fractions with the same denominator. In this case, though, what we're going to do with that denominator is we're going to multiply both sides of the equation by it so that all of the denominators disappear. And then we'll be left with either a linear or a quadratic equation, which we will solve, and then we'll need to check and make sure that the solutions to that linear or quadratic equation are actually solutions to our original equation. Alright, so here's an example. We have 4 over x squared minus 3x minus 1 over x squared minus 9 equals 0. Okay, so the first step is to factor the denominators. So the first denominator, both terms have an x, so we can factor out an x. And in the second denominator, we have a difference of squares, x squared minus 3 squared. So we can factor that denominator as x plus 3 times x minus 3. Okay, so the second step is we want to multiply both sides by something that will get rid of all of the denominators. So this is kind of analogous to something we've done before. So if you had, for example, x over 4 minus x plus 2 over 6 equals 5, for example. You would possibly want to multiply both sides by something that will get rid of the 4 and the 6 for your denominators. So you choose the least common denominator. In other words, what is the smallest number that will clear both of those denominators? Well, 4, if we factor that, is 2 times 2, and 6 is 2 times 3. So we choose 12 because it has 2 factors of 2 to get rid of the 4, and it has a 2 and a 3 to get rid of the 6. So that's essentially what we're doing here. It's just our denominators aren't numbers anymore. They are expressions that have a variable. So basically, if a factor shows up in any of the denominators, we want to multiply by that factor. If it shows up twice in the same denominator, we'll need to multiply by it twice. So for example, here if we look at our first denominator, there's a factor of x, so we need to multiply both sides by x, because then that will get rid of the x factor in the first denominator. Our first denominator also has a factor of x minus 3, so we'll need to multiply by that. Now since we have this minus sign on the left, whatever we multiply by is going to get distributed to each fraction. So we're going to have cleared the first denominator with what we have already, but it's also going to get distributed to the second fraction. So this x minus 3 factor will take care of the x minus 3 factor in the second fraction as well. We just now need also to multiply by x plus 3. And now we will have taken care of both denominators. Alright, so we're multiplying both sides by x times x minus 3 times x plus 3. And like I said, that's going to get distributed into both fractions on the left. So I'm going to write out that step. After a while you might find that you don't need to, but a lot of people do find it helpful. So remember that we're multiplying by all of this stuff over 1. So that's why our denominator is not changing, because we multiply the numerators together and we multiply the denominators together and we get what we started with in the denominator since we're multiplying by 1. Now we're multiplying the right side by this same stuff, but the right side was 0, so it's still going to be 0. And now we have some factors that will simplify. So we have x over x here. We have x minus 3 over x minus 3. And in the second fraction, we have some x minus 3 and x plus 3 factors that will divide out. So we've eliminated both of the denominators. So we're just left with 4 times x plus 3 minus x equals 0. And then we can just solve that equation for x. So we'll distribute the 4. Combine our like terms. Subtract 12. Divide by 3. So we end up with x equals negative 4. Now that is definitely a solution to this linear equation that we ended up with, but we need to check and see if it's a solution to the original equation that we were solving. So the big thing we need to check for is if we substitute the number for x, do we get any denominators that are 0? If that's the case, it can't be a solution, because when we substitute a number for x, if it's a solution, we should get a true statement. And a true statement meaning both sides really do become equal. And the two sides can't be equal if one of them is not a number, which is the case if the denominator is 0. But anyway, if we substitute negative 4 here for x, none of the denominators become 0. So we will get a true statement. The left side will simplify down to equal 0. And so negative 4 is a solution. Alright, here's another example. We have x over x minus 2 plus 1 over x plus 2 equals 8 over x squared minus 4. Okay, so our first step is to factor any denominators that can be factored. So the two denominators on the left cannot be factored because they're already linear. But we can factor the denominator on the right. The denominator on the right is the difference of squares. It's x squared minus 2 squared. So it's going to factor as x minus 2 times x plus 2. So now we need to decide what are we going to multiply both sides by to clear our denominators. So if we look at the right side, definitely need to multiply by x minus 2 times x plus 2, because that will get rid of the denominator on the right side. And whatever we do to the right side, we also have to do to the left side. And it turns out that's enough, because we have an x minus 2 factor to get rid of our first denominator on the left, and we have an x plus 2 factor to get rid of our second denominator on the left. So we're going to distribute this in. If you don't want to write out the extra step of distributing in, that's fine. Just keep in mind, if you like to physically cross out factors as you simplify, you don't want to cross off the x minus 2 when you're working on the first fraction, because that x minus 2 does still need to be multiplied by the second fraction. So just be careful of that. It never hurts to write out more than is necessary, just to make sure you don't lose track of things. Okay, on the right side I am going to simplify this at this point, so we just get 8 on the right. And then we can simplify our fractions on the left. So we have x times x plus 2 plus x minus 2 equals 8. And then we'll solve that for x. So we'll distribute the x here. And we'll combine our like terms there. So in this case, we end up with a quadratic because we have an x squared term. So we talked about several methods for solving quadratics. A lot of them require it to be equal to 0. So we'll do that. And that left side does factor. I'm going to omit those steps here. But it factors as x plus 5 times x minus 2. So this quadratic equation has two solutions, negative 5 and positive 2. However, we didn't start out with a quadratic. Anytime you end up with a different type of equation than what you started with, it's a good idea to check the solutions because some of them might not be solutions to the original. So these are the solutions to the quadratic, but are they both solutions to our rational equation? So if we come back to our original equation here, we see that if we put 2 in for x, we get a denominator of 0. So 2 can't be a solution because substituting it in doesn't result in a true statement. 2 is not a solution. However, if we substitute negative 5 for x, none of the denominators become 0. So negative 5 is the only solution to the rational equation. This solution that we got that was a solution to the quadratic but is not a solution to our equation is often called extraneous. Extraneous, like extra. We've got an extra solution that's really not a solution to our equation.